Okay, folks, let's do this. Last time I left off with the alchemistry, we were looking at... Nope. These examples. Alright, I guess one day I'll figure out which way to actually point. We're looking at these examples, right? Chemical and physical changes and properties. A little, basically practice of checking your phase changes versus your chemical change words, right? You know your phase change words. You see melting, you see evaporating, you see freezing, right? Those are phase changes. They go from solid to liquid, liquid to gas, or the other way. And then you have your chemical change words. Burning, corroding, rusting, decomposing. Electrolysis, combines with, reacts with. Remembered them all that time. Alright. Anyway, let's take a look at these. Alright. So for the first one, we're trying to just label, is it chemical or is it physical? So look at my keyword, evaporating. That is a phase change. It's physical. Again, look at my keyword, melting. And melting. Whether it's butter or copper metal, they are both physical changes, because all you're doing is so with a phase change, all you're doing is you're taking those particles and you're making them further apart or you're making them closer together. That's it. That was the difference if you look back at our particle diagrams. That's the only difference. The solid particles are really close together, and then the liquid particles get a little further apart, and the gas particles get even further apart. But that's it. It's the same particles, same little orange dots here, right? Okay. Now, I don't need to zoom in that much. There we go. Now, mixing. You know what I should do? Instead of doing that, I should just highlight, right? Melting, evaporating, mixing, and burning. Those are our big key words. Now, mixing is pretty physical. Mixing sugar into water. Sugar, water, mix. That's physical. But burning something, that's a chemical change. Because when I burn wood, after I burn wood, I no longer have wood. I have ash, I have soot, I have smoke, I have fire. None of which is wood. So I've changed what I have. Chemically, I've changed the composition of what I have. It's not the same substance. It doesn't have the same properties anymore. It's fundamentally different from the way that it was before. Number 2 asks us, which of the following is not a physical change? So which of the following is chemical? So let's look for our words, right? Freezing, melting, burning, boiling, and tearing. Of those words, burning is our chemical change word. Freezing, melting, and boiling are phase changes. Tearing is ripping something apart, still aluminum foil. Again, is not a physical change. So, again, is chemical. So we have our keywords, grating cheese, melting cheese, mixing cheese. Well, those are all physical. But when cheese gets moldy, the reason it gets moldy, the reason it gets gross, is because there's a chemical change happening. Alright, I'm going to identify the chemical changes here. I know that burning is chemical, corroding is chemical, react with is chemical, rusting is chemical. That means that all of these other ones, phase change, phase change, phase change, phase change, crushing, that's a physical change. One might use the word pulverizing, but it's a physical change. If a mixture is homogeneous, so here's my keyword, homogeneous, which is something like instant lemonade, or chocolate milk, salt water, right? The physical properties and composition. If I had a glass of chocolate milk and it was properly mixed, right? No extra bonus chocolate syrup at the bottom of the cup. Well mixed chocolate milk. And I took a small sample from the top, I took a small sample from the middle, and I took a small sample from the bottom. They should not be different from one another. They should not vary. They should be the same in every element of the sample. Remember, homogeneous is called homogeneous because it's the same throughout. If it varied, if you could tell a difference in the composition of the mixture, it would be heterogeneous, something like Chex Mix. Alright. And then finally, chemical or physical again. So, bust out my highlighter. I have liquefies and I have burns. Liquefies is a fancy word for melts. It turns to a liquid. And burning, we know, is a chemical change. Alright. Easy peasy. Hopefully. I hope. Now, what I'd like to do... Oh, not that. Don't do that. I'd like to finish page 9 here. I'd like to do these two conversions. And then I'd like to take a look at the reference table. Well, 2 looks at the reference table, actually. We'll start with 1. Now, when we left off talking about energy, we mentioned that it was like our ability to do work. How much heat can this fuel produce? We have kinetic and potential. Those are our main 2 types of energy. And our unit for energy is the joule. Yep, the joule. Anyway, we have another law here. And it's the law... Oop, that's not a V. It's the law of conservation of energy. It also doesn't really look like an R. Alright, apparently I'm writing this whole word over. Conservation. The conservation of energy. You don't make energy, you don't destroy energy. It just changes from one form to another. So when I said before that I lift a book over my head and then I drop it, when I lift it over my head it has potential. It could do something. And the moment I release it, it goes from potential and it becomes kinetic. And more kinetic as it falls to the ground and then slam into the ground. And the reason you know it slams into the ground is because you hear noise. They have sound energy. Something that we don't talk about in chemistry. It doesn't have to do with a chemical reaction. It's physics. It's next year. Take my class again. Anyway, conservation of energy. Now, this is already starred, but I want you to highlight this. This is a definition. I'm going to abbreviate temperature, but you can write out temperature, the whole word. Temperature is a measurement of the average kinetic energy of the particles in a substance. Temperature itself is not actually energy. It's a way that we measure the average energy of an object. A higher temperature means that that object has a higher average kinetic energy. Its particles have a higher average kinetic energy, which should make sense. The faster something moves, generally the warmer it gets. The slower something moves, it's because it gets cooler, right? There's some correlation there. Now the SI unit of measurement for temperature is actually... that's not an I. Kelvin, which is a unit of measurement you may not have seen before. It's not degrees Kelvin, it's just Kelvin, right? Now, yeah, there's no degree symbol. The 0 point of Kelvin is negative 273 Celsius, which is negative like 500 something, maybe 600 Fahrenheit. It has a very unique term. We call it absolute zero, and it's the point at which all particle motion completely stops. Everything, even ice particles are frozen solid. Now we say solid. What we mean is that the particles are moving slowly enough that they're able to hold a form. The colder you make something, the slower you make those particles move. If you slow them down enough, if you lower the temperature enough, if you take away enough heat from something, you can get it too close to absolute zero. And we haven't gotten quite to absolute zero. We're almost there. There are entire teams of scientists dedicated to looking at absolute zero, because things do really weird, like substances, act and behave strangely near absolute zero. One of my good friends was involved with the study of a conductor near absolute zero. And it's fascinating. A lot of it went over my head. I understood a little bit of it, but scientists are fascinated by this because it's completely wackadoodle. It's kind of fun. It's nice. Right now, there is a conversion from Kelvin to Celsius. You subtract 273, and it says see reference table T. So what I'd like to do is, very quickly, see reference table T. This is reference table, table T. It's the last page in the reference table, and right here at the bottom, we have our conversion from Kelvin to Celsius. If we need Kelvin, and we have the Celsius degrees, we simply add 273. That's our measurement temperature in Kelvin. Similarly, if we have our temperature in Kelvin, we need to go to degrees Celsius, so we simply subtract 273 from both sides. Runner. And, sorry, some stuff fell on my desk. And we have our temperature in Celsius. Alright, this is not something you need to memorize. Look, it's on your reference table. It's lovely. Now that in mind, these are very straightforward. If I look at this, then Kelvin is Celsius plus 273, which means that this Kelvin temperature, which means that 50 Kelvin equals degrees Celsius plus 273, which means I need to subtract 273 from both sides. That goes away. And that means that my degrees Celsius is negative 223 degrees Celsius. Similarly, 150 degrees Celsius plus 273, well, that's what Kelvin equals. 150 plus 273 is 423 Kelvin. Notice, no degrees in Kelvin, just Kelvin, straight up. Alright. Last thing I wanted to do today has to do with page 11 of our notes, the next page of our notes, and talking about the periodic table. Now, the periodic table is something that we find on our reference table, and I've rotated this clockwise because it allows me to look at the reference table much more easily. Now here's the reference table, here's the periodic table as we know it. Many symbols, lots of information here. All we're going to look at for now are the symbols and a correlation to this atomic number. You'll notice that this atomic number, this number in the bottom left corner, the bolded one, it goes up. It's 1 here, and then 2. We move to 3, 4, 5, and so on. Alright? Why I'm bringing this up is because if we're looking at this, right, the periodic table is one way to know if something can be identified as simply an element or as a compound. Notice that many of the elements are single letters, H, B, C, N, O. Some of them are double letters. When there are 2 letters in the symbol for an element, the second is always lowercase. It's uppercase, then lowercase. Right? That's important for identifying because something like this is classified as an element. Something like this is classified as an element, but there are 2 capital letters here, C and O. 2 capital letters means that this is a compound, right? We talked about, this is kind of related to this little exercise up here, right? Now, what I'd like y'all to do here is spend some time getting used to looking at these symbols and getting used to looking at these names. The symbols are all here, physically on the periodic table of the elements. But on the pages following, you have the atomic number, again, this bolded number, the bottom left. You have the symbol, and then we have the formal name. Right? There's a lot more information here. We're not going to look at it yet. All right? All I want you to do is familiarize yourself with being able to translate the symbol into the name, or perhaps translating the name back into the symbol. Alright, that's page 11 here. The next thing that we're going to get into is breaking down some of the rest of these numbers, the atomic mass, atomic number, the electron configuration, right? We're going to focus on the left side first, then we'll move over to the right side. That's kind of just the way it works out. It's kind of nice because we read naturally from left to right. Our next piece, the next thing that we're going to look at, is how, even though I said here in the notes that an element is a substance that cannot be broken down into simpler substances by chemical change, that's only mostly true. However, that is an issue for tomorrow's class. Alright? If you'd like to get a little ahead, well, let's not get ahead of ourselves. Make sure that your notes are filled in all the way through page 9, bottom page 9 here. There is a moment on page 4 where we talk about percent error, and it is currently blank. That was intentional. I apologize if anybody is like having a little mental misstep because we have skipped that. I have skipped it intentionally. There's a lab that I'd like to do that goes along with it. I think it explains it nicely. I'm working on finding a digital copy of it because I fear that we will not be able to do it physically, whether you are fully remote or hybrid. I don't even know if the hybrid learners who are in school every other day will be able to do it, but I'm hoping we can. If we cannot, I think I found a digital version that I like, but percent error is incomplete. So as of right now, everything in your notes should be filled in all the way through page 9, except for that little section of page 4. Alright? Page 10 was all examples. 11 is examples that I would like you to do today, before the next A-Day, right? I think what I'm going to also do before the next A-Day is put up another little video. It'll be shorter than this because I'll only do notes. It'll be no examples, it'll just be notes. And it will be the beginning of the next set of notes. Look for it in the next topic on my CBA. All that being said, I have again rambled on far too long. I apologize for making these videos a little longer than they should be. I'm going to work on cutting myself back, giving myself a time frame to work in. Right? In the meantime, I will see you soon, kids, but be good, stay sane, and please, please, most of all, stay safe. Take care.